Section 1.8 is from Chapter 1, and it's a review that we'll need before we go into the trigonometric inverse function. So it's just a little review of inverse functions. Before we can talk about inverse functions, we have to talk about one-to-one functions. So the first thing we need to be able to do is determine whether a function is one-to-one. And this is going to be an important point when we go back to Chapter 3. Then we're going to determine the inverse function, the inverse of a function. Defined by a map or a set of ordered pairs. So this should all be review from algebra. Number 3 is to obtain the graph of the inverse function. From the graph of a function. And number 4 is going to be find the inverse of a function. Defined by an equation. So number 1 is determine whether a function is one-to-one. And hopefully you read the instructions on the last page of the first exam you just took where it said on the matching, it's not necessarily a one-to-one correspondence. There could be more than one thing that matches to more than one thing. So I'll have a function sheet that I'll hand out to you in class, and we'll talk about how do we tell if a relation is a function, and we'll look at a lot of examples because I think that's the best way to get the idea. So it's a two-step process. First, you have to decide whether the relation is a function. We're trying to decide if a relation is a one-to-one function, sorry. Then if the relation is a function, test whether each output originates from only one input. So to be a one-to-one function, you first have to be a function. So that's the vertical line test. So remember when you learned about the vertical line test, you said if every vertical line that goes through this function graph hits it only once, then it is indeed a function. But this is not a one-to-one function because when I make a horizontal line here, I run into the graph multiple times. So some circle is a graph and it has an equation that defines it, but it is not a function. It doesn't pass the vertical line test. So you don't even have to use the horizontal line test because you can't be a one-to-one function if you're not even a function. So let's look at a graph that is a function because every vertical line hits it only once, and it is one-to-one because every horizontal line hits it only once. So let's look at this ordered pair function, and remember that these are just dots, the 0.13, the 0.25, the 0.37, and the 0.49. This is the graph of this function. It is just dots. Another way of looking at this is if you have a map, if you have domain and range, and this is what we talked about earlier, if I have a domain of 1, 2, 3, and 4, and a range of 3, 5, 7, 9, and 1 goes to 3, 2 goes to 5, 3 goes to 7, and 4 goes to 9, this is a function. Since each input has one and only one output, and it is one-to-one, because if we look backwards, each output came from one and only one input. So this is a one-to-one function. Okay, so let's look at this one. If I have 1, 3, so I'm going to make a map again with domain and range. If I have 1, 2, 3, and in the range 3, 4, 5, 7, and 1 goes to 3 and 1 goes to 4, 2 goes to 5 and 3 goes to 7. Let's see, we got a problem here because this isn't even a function. because you have one input going to two outputs. So let's look at this next one. And I'm going to make a map again. I find it easier to visualize with a map. So my domain is 1, 2, 3, 7. My range is 3, 5, 9. 1 goes to 3 and 2 goes to 3. 3 goes to 5 and 7 goes to 9. So this is a function. Every item in the domain goes to one and only one item in the range, but it's not one-to-one because we have this item in the range that came from two different items in the domain. So in order for the graph of an equation to be the graph of a function, the graph must pass the vertical line test. And I showed you some examples of, here is one that passes the vertical line test. Here is one that doesn't. But for a graph to be the graph of one-to-one function, it must pass the vertical line test to be a function and the horizontal line test to be one-to-one. So if every horizontal line intersects the graph of a function and at most one point, then f is one-to-one. So this graph is not one-to-one. It is a function, but not one-to-one. And then this graph is the graph of a one-to-one function. Passes the vertical line test, so it's a function. Passes the horizontal line test, so it's one-to-one. Okay, so logically, how you write this is that f of x1 has to not equal f of x2 whenever x1 doesn't equal x2. So what you're saying is if you have one value of x and another value of x, that you can't have the same y values for two different x values. This would not be one-to-one. A function that is always increasing or always decreasing is one-to-one. That seems pretty obvious, doesn't it? We'll prove it later in calculus. But if you're always increasing, you have to pass the horizontal line test because every y value is larger than the previous y value from the x value to the left. Okay, so determine the inverse of a function defined by a map or a set of ordered pairs. So we've been looking at some of those already, but let's get more specific. So you first ask, is it a function? And then ask, is it one-to-one? If the answer to both of these questions is yes, the function has an inverse. And this is a provable theorem that guaranteed you have an inverse. So we write the inverse function, recall, as f inverse of x. So this is not equal to 1 over f of x, if that's what you mean. So f inverse of x does not mean this. If you want to write 1 over f of x, you would have to put grouping symbol of brackets around the f of x with an exponent of -1. So this isn't really acting like an exponent of -1, it's just a symbol saying the inverse function. And you're already familiar with a lot of inverse functions. So if your function is x cubed, then your inverse function is the cube root of x. So suppose I have 34 people in my Math 8 class, 38 in my Math A class, 37 in Math 31, and 39 people in Math 42. Is this a function? Yes, because each item in the domain maps to only one item in the range. And it's one-to-one because each item in the range came from only one item in the domain. So yes, it has an inverse. So what does the inverse look like? It says the class with 38 students in it is Math 8. So do you see how it's like going backwards on the map? The class with 34 students in it is Math A, and so on. Okay, so here's an example with ordered pairs. If your F looks like 1 maps to 3, so let's do a domain range map again. 1 maps to 3, 2 maps to 5, 3 maps to 7, and 4 maps to 9. Then the inverse function takes 3 back to 1, and 5 back to 2, and 7 back to 3, and 9 back to 4. So that's the inverse function. So it's pretty straightforward. So notice that the domain of F is the range of F inverse. And the range of F is the domain of F inverse. So if we write the notation F inverse of F of x equals x, this x has to be in the domain of F. So x is in the domain of F of x. But F of x is an element of the range of F of x, which is also the domain of F inverse of x. But when we write this notation, F of F inverse of x equals x, this is a different x, and this is a key point for what we're going to do in chapter 3. This x is in the domain of F inverse. So this means it's in the range of F. And F inverse of x is an element of the domain of F. So I want you to think about that and work on it until it makes sense to you. It might take a while. So to verify that functions are inverses of each other, we show that f of g of x equals x and that g of f of x equals x. And you have to do both. So you show that if you compose. So remember we talked about composing f of g and g of f. This is the same idea as composition. So I'm going to start here on a second movie so that I don't run out of time.